I'm Masao Sakane from Ritsumeikan University, Japan. And these three guys are a colleague at the same university. And Mr. Tokuda is IHI Technology. This is a joint project with Ritsumeikan University and IHI Corporation. Today, I'd like to talk about how can we extract a clip material constants from the indentation test, especially from the P91 steel under creep damaged material. But this is the normal flow of my presentation. Skip that one because of the time restriction. It's a little bit hard to observe, but this is a weld joint of P91. And this part is an parent material. And this part is weld metal. In between two metal materials, there's a heat affected zone called as HAZ in short. And we're going to try to create material constant of parent material HAZ and weld metal in that situation. Not using a simulation heat treatment. Much easier. So far, there are many experiments were done to make to use a simulated HAZ material under creep, but it's a little bit time consuming and costly. So we're gonna try to extract the creep material constant in this situation. But we have to solve two questions to make that one. The first one is how to convert the indentation creep to a uniaxial creep material constant. The second one is there's no commercial based machine available to make such kind of test. So we have to develop such kind of indentation creep test stepwisely. Okay, I will talk about the first three in very short, how to convert the indentation creep result to a uniaxial creep result. Okay, look at this left here. The ball is pressed to the material and the temperature is raised, so the H, H is penetration depth is increasing as the second figure. The ordinate of the second figure is the indentation depth against time. And in this situation, and the S is the production area, and the indentation stress is defined P over S. And the indentation strain rate is defined from this curve as H1 by H dt over dH. And if we plot this indentation stress and the indentation strain rate, we can get stress and strain rate like this figure. But this line is different from the uniaxial creep because of the multiaxiality of beneath the ball indentor. So we have to convert. We have to develop the convert method to indentation this result to uniaxial one. And they're a little bit complicated equations, but we can do it for Norton's law. Maybe you know where about the strain rate is alpha sigma proportional to beta. And as I told you, indentation stress is given by this equation. The strain rate is given by this equation. And we got this line. And if we assume that an alpha and beta is a uniaxial data, we have to convert alpha indentation from the data of alpha indentation, beta indentation to alpha and beta. And by using these equations, very fortunately, beta is agreed to the beta indentation. The alpha can be calculated by this equation. So we have already published this result in this paper. If you are interested in this procedure, please look at this paper. And unfortunately, P91 shows a sine hyperbolic law. Shows a sine hyperbolic law. So in this case, the similar procedure can applicable, and then we can really extract the alpha A and B from the indentation test. And the second question is that how can we get data? So we invented this machine. This is a stepwise indented machine, and specimen is set here at the top plate. And we use the ball indenter. And the applied load is driven by this motor, actuator. And load applied to the specimen is measured by this load cell. And the indentation depth were measured by 2 LVDTs. And this machine has one device because, okay, we will make a first indentation test and remove the load and up the indenter and slide the specimen and again make an indentation. So we can make 5 or 6 indentation tests by one operation. That's a very good point. The left figure is on a photograph, very small size, just 250 millimeter and 500 millimeter. It's a tabletop type machine. And the specimen was heated by the furnace surrounded by the specimen. Okay, this is the material we have used. This is a usual P91 heat treatment. And joint specimen, well, mainly we had made 3 tests. This is a parent material, heat affected zone, and welded metal. Joint specimen, later I will mention, is cut out from here. This joint specimen across the parent material, heat affected zone, and welded metal. This is joint specimen. And the welded specimens that tested the welded metal. And the welded specimen vertical were taking place in this direction, the vertical direction. And the horizontal welded specimen is horizontally taken. I want to remind you that the joint specimen and the welded specimen has a different heat treatment. Joint specimen has had a very standard PWHT post-weld heat treatment, 740.7 hours. But welded metal specimen was a little bit overaged. So that specimen will gives a little bit softer. I'll skip this one. What's this? No. Sorry. Okay, that's the story I told you. The specimen size is 15 millimeter and 10 millimeter height. Thickness is 10 millimeter. Joint specimen, welded vertical specimen, welded horizontal specimen. So you can look at the small circle. This is the stand after the test. So 1, 2, 3, 4, 1 to 6. Okay. Skip this one. This is the measurement result we got so far. Okay, this is a joint specimen. The left side, this specimen across the parent material heat affected zone and welded metal. Before making an indentation creep test, we measure microviscous hardness against that is the stamps we have made. And this is the hardness of the parent material, and this part will be heat affect zone. And this part is a welded metal. And 1, 2 is a parent material. 3 is an heat affect zone. 4, 5 are welded metal. Okay, let's look at the results. 1, 2 is the indentation depth and time. 1, 2 gives a similar trend. It's a base metal. 3 shows a much soft response because of fine grains has. And 4, 5 is a welded metal. It's much harder. This is and we plotted the low plot, and 1 to here, 2 is softer, 4, 5 is harder. And we converted this to a uniaxial one, and 1 is here, 1 is here. And you can find the 4 hollow dots. This is the uniaxial data of the parent material. It's a little bit softer than the original parent material. And look at the 3. It's a has. It's much softer. And this curve is not curve, it's a straight line. So different response of the base metal and the heat affected zone. And look at the 5, 4, it's the welded metal gives much harder responses. So we can get the constitutive equation of these 3 parts in one experiment. It's very important and very efficient and time efficient. Okay, this is an horizontal welding horizontal. This specimen, we tested the 4 stamps, 1, 2, 3, 4. So almost the same response we have had. And then this welded material is a little bit overaged, as I told you. The welded metal, even welded metal gives a soft response than the parent material. It's a little bit surprising. So we believe that the welded metal is harder than the parent material, but it's the long time exposure at high temperature where it's going to softer. And at this thermal treatment condition, so welding metal gives a much softer response than the parent material. Okay, this is maybe the last slide. This is a horizontal specimen. Well, this is not expected as before. The horizontal welded specimen gives a much scatter than the horizontal vertical. Why? Because the welded metal was the layer over layer. So in this direction is a uniform, but in this direction, the layer, and across in between the layers. So that gives a little bit scale. Oh, yeah. Maybe I hope you can understand my talk. So I will skip my conclusion remark. Thank you very much.
Thank you, Sakane.